take up the divergence of a vector field. Vector field की example आपके पास है. The velocity of a liquid through a tube, electric field, gravitational field, magnetic field. तो normally जब भी हम एक vector field को express करते हैं, we express it with the help of some kinds of lines. जैसे we have magnetic lines of force, we have electric lines of force, and in case of a liquid passing through a tube, we have the streamlines or the velocity lines along which the molecule moves. Now, how we define divergence of a vector field? Given a vector A, we define it as the dot product of del operator with the vector A. So obviously, the outcome of this operation will be a scalar. That way, divergence of a vector field is a scalar quantity. And if I write del operator dot A and assume that this vector A has the component, so vector A is equal to ax I cap plus ay j cap plus az k cap. So this del dot A would be equal to I cap dou over dou x plus j cap dou over dou y plus k cap dou over dou z dot. So I am taking dot product of this dot. So I substitute A here. It is ax I cap plus ay j cap plus az k cap. So while we take the dot product, we multiply I dot I, which is 1, j dot j is 1, k dot k is 1. So this result would be dou over dou x of ax plus dou over dou y of ay plus dou over dou z of az. And this is definitely a scalar quantity. And as mandatory practice, जब भी हम एक del operator के सामने function को रखते हैं, we don't write it here, उसके components को उसके सामने रखना है. So with this, we have seen that how we can make a mathematical operation for finding divergence of a given vector field. It will come out to be a scalar quantity, and that scalar quantity you can give the divergence equal to. How we interpret divergence as a property, उसके लिए हम एक थोड़ा सा example एक ले लेते हैं. Let's illustrate the divergence of a vector field by assuming a liquid passing through a certain region of space, क्योंकि जो उसका velocity field है, that is definitely a vector field. So ये Cartesian plane है. I have x, I have y, I have z axis, and here I imagine a very small parallelepiped. So here is a parallelepiped. So this is the parallelepiped. We have exaggerated the size, लेकिन imagine कि जो उसका ये एक edge है, this edge is dx, parallel to x-axis. This edge is dy, parallel to y-axis, and this edge is dz, parallel to z-axis. I imagine a point in the middle of this parallelepiped. I call it as point P. And this point P has a fluid arriving from this phase towards this phase. अगर हम उस fluid की velocity का जो velocity हम v assume करेंगे, अगर हम उसका x component लें, then that x component will be along the x-axis. So I assume कि जो point P है, अगर यहाँ पर point P पर जो उसका x component है velocity का, वो है vx. So you will agree with me that if I go beyond this point to the left and I touch phase 1, ये इसका phase 1 है, और ये इस small volume का phase 2 है, the value of velocity at phase 1 will not be same as vx. It will be slightly different, and if I go forward, it will be slightly different. Now we think of the volume flowing through a certain phase per second as something like this. जब आप area को multiply करते हो velocity से, so area multiplied to velocity becomes, So area is distance covered per unit time. So it is distance covered by time, and velocity is distance covered per unit time multiplied by area. So area multiplied by distance would be volume. So this becomes volume flowing out per time. So that way, this volume flowing out per unit time, इसको हम rate of flow भी कहते हैं. In case of fluid dynamics, we call it as rate of flow. So think that the velocity of the liquid here and velocity of the liquid here, if multiplied to the perpendicular surface area of the given phase, can give us the volume flowing out per unit time. So if I say volume flowing per unit time at phase 1. Phase 1 आप देख लें, this is phase 1 shaded, so this is phase 1. So I'll take the velocity जो इस shaded area के perpendicular है, that velocity here is the velocity along x-axis. So let me call it as Vx, और ये Vx इस point पर कितना होगा, that I can find like this, कि अगर ये Vx यहाँ है Vx, here I say that it will be Vx minus change of Vx with respect to x. So this you have to understand कि I have taken it as a partial derivative, क्योंकि जो velocity है ये असल में 3 डायरेक्शन में बदल सकती है, along x-axis, along y-axis and along z-axis. So I take here the rate of change of velocity with respect to x-axis and multiply it, क्योंकि सेंटर में ये Vx था, ये Vx इसके सेंटर में था. How much it has changed towards the left face is that I find rate of change of Vx with respect to x and multiply it by delta x by 2. How come delta x by 2? क्योंकि इस पॉइंट से लेके यहाँ तक का जो डिस्टेंस है, that is half of this delta x, so I can write as dx or delta x, so I call it as delta x by 2. You may call this as delta x, you may call this as delta z, and you may call this as delta y. So this becomes the velocity at the left phase. Now if I have to find volume flowing out per unit time, तो मैं इस velocity को multiply कर देता हूँ with the area of this phase, which is delta y into delta z. I can also find volume flowing out per unit time at phase 2. अब देखिए, अगर यहाँ velocity v minus something है, तो जब ये velocity इधर की तरफ होगी, so let's say the velocity will change, it will become Vx plus rate of change of Vx with respect to x multiplied by the distance traveled from center P to the phase 2, so that is delta x by 2 multiplied by delta y by delta z, because this phase also is perpendicular to the x-axis. तो ये जो velocity यहाँ है, it is like this, ये इसके perpendicular. Now this gives us a difference of two velocities. So if I have to calculate that how much would be the net volume flowing, so I can say net gain in volume per unit time. So per unit time, so it will be the difference of these two. जब आप इनका difference लेंगे, you can take delta y, delta z common. From that you can subtract these two. तो जब आप इनको subtract करोगे by opening the brackets, you will have Vx plus delta dou over dou x of Vx into delta x by 2. तो इसमें से ये subtract करना है minus Vx. तो जब आप इसको subtract करोगे this minus this, ये minus into minus plus हो जाएगा, plus dou Vx by dou x into delta x by 2. So once you make this operation, Vx and Vx will get cancelled. तो ये दो आपस में add हो जाएंगे. So your result will be delta y into delta z is common outside. So this will be twice of this. ये twice इसके साथ cancel out हो जाएगा. So that will be twice of dou over dou x of Vx into delta x by 2, तो ये 2 और 2 कैंसिल आउट हो जाएगा. फाइनली इट इज dou over dou x of vx multiplied by delta x, delta y, delta z. Now we have assumed that the whole liquid is moving along x-axis, and we have found the volume flowing or the net gain in volume per unit time along x-axis. We can similarly find the net gain in volume per unit time along y-axis. Along y-axis. You can repeat the procedure and your result will be dou over dou y of Vy multiplied to delta x, delta y, delta z. You can also find net gain in volume per unit time along z-axis, which will be dou over dou z of Vz multiplied to delta x, delta y, delta z. Now this can give you the sum total of all the three, and if I say net gain in volume per unit time in all directions. When I say all directions, it includes all the three directions, so that would be that you have to add these three, so that is dou over dou x of vx plus dou over dou y of vy plus dou over dou z of vz and multiplied by, I have taken delta x, delta y, delta z common, so this is delta x, delta y. Find now the total gain in, so total gain in volume per unit time per unit volume by fluid. So that would be equal to, now I have to divide this by the given volume. So this was for the volume delta x, delta y, delta z. So that way I have this as my answer when I divide this quantity by delta x, delta y, delta z. तो यहाँ पहले मैं इसको मल्टीप्लाई कर देता हूँ डेल्टा x, डेल्टा y, डेल्टा z से, फिर मैं इसको डिवाइड कर देता हूँ because I am finding it now per unit volume. So this is delta x, delta y, delta z. This cancels out. So this is your answer. Now this is nothing. It is simply कि अगर आपने देखा कि when we find the result del dot v, so v is the velocity. It has components vx, vy, vz. So that answer comes out to be this. That way, what we have found that divergence of a liquid or divergence of a vector field. We can generalize this result now. जो divergence है vector field का, that is nothing. It is that how we find the value of this dot product of del operator with say here we have used velocity, but we can generalize it for any vector field. V is now any vector field. So this is the answer that divergence we get. अब यहाँ पर तीन केसेस राइज करते हैं. If it happens so कि जब लिक्विड हम इस स्मॉल वॉल्यूम में एक्सपैंड करता हुआ देखते हैं, it becomes a source of the liquid, then divergence will be positive. If the liquid is instead of expansion, it contracts. That means जो ये लिक्विड का रीजन है, इस रीजन में लिक्विड इससे जो एक्सपैंड के बजाय जब कंट्रैक्ट करता है, और that contraction makes it the sink. In other words, instead of giving us the source, it becomes a sink for the liquid. The divergence will become negative. If it neither way happens कि ना ही ये expand कर रहा है, ना ही liquid यहाँ से निकल रहा है, और ना ही ये liquid को से एक तरह से sink कर रहा है या liquid को ये खींच रहा है, it becomes a divergence-less region. A divergence-less region has the significant property that for a divergence-less region or a divergence-less scheme divergence less the dot product of vector, say here the vector is V, with del operator, which you call as divergence of the vector, becomes 0. Such a field, a vector field which shows this property, is called as solenoidal also. Now what solenoidal actually is, that in case of a solenoid, if we see the magnetic flux entering and the magnetic flux leaving, they are equal. So there is no gain, there is no loss, so it becomes a solenoidal or a divergence-less region. So ये इसका physical significance है divergence का, and you have seen how you operate with the del operator to find divergence. If you are given a vector, differentiate that vector, उसके components को आप differentiate कीजिए, x component को x के साथ, y component को y के साथ, z component को z के साथ, add the 3, that gives you the answer. Your answer will be always a scalar, which will be either positive or negative or 0. Some problems will appear at the end of this lecture, which you can solve for understanding this concept further. We take up now curl of a vector field. So it is defined for a vector field, and del operator combining with a vector field in this manner. Suppose I have a vector A, and curl is defined as the cross product of vector A with the del operator. So this will be read as curl A. We are already aware of the del operator, we are already aware of A. So if we see that del operator is I cap into dou over dou x plus j cap into dou over dou y plus k cap into dou over dou z, then A vector is equal to axi cap plus ay j cap plus az k cap, and then we can think of this curl as the determinant, which I will develop like this, that this determinant whose first row is I cap, j cap, k cap, then we have dou over dou x as the components of the first vector, that means जो इस product में पहले आएगा उसके components को पहले लिखा जाएगा. So these are the components of del operator, और फिर इसके components जो हैं a x, a y और a z express किए जाएंगे. So this determinant is actually the determinant which represents curl of vector A. So we expand this determinant and we can get the components of the curl like this. So let's say we expand the determinant with respect to the first row. So I have del cross A. So del cross A would be first row, first element I cap into. So cut the column, cut the row. So we have its cofactor, first row, first column. Now cut the column, cut the row. So this would be dou over dou y, and then dou over dou z. Here you have a y, a z. Then go to the second element. This gives you j cap, first row, second column, first row, second column, cut the column, cut the row. So that gives you dou over dou x, dou over dou z, and here you have ax, az. Then you have the third element, that is k cap minus 1, first row, third column, cut the column, cut the row. So that gives you dou over dou x, dou over dou y. Here you have ax, ay. You can further expand it, so we get I cap into, यहाँ देखिए ऑपरेटर के सामने ही फंक्शन को रखना है. So that way this would be minus 1 raised power 2 will be 1. So this will be dou over dou y of az minus dou over dou z of ay. Similarly, you can go to the next. So ये हो जाएगा minus j cap into, so that would be az minus Here it will be again plus, so it is plus k cap into, so this should be so this is the result. अब देखिए इसमें तीन कंपोनेंट्स हैं, there is I component, that is X component, there is Y component, there is Z component. तो अगर हम del cross A curl of A का X component लेते हैं, so this would be the X component of this X component, so that would be equal to, ये आपके पास होगा I cap into dou over dou Y of AZ minus dou over dou Z of AY. You can also find its Y component. So Y component of curl A, this would be equal to Y component of curl A Y component would be equal to, तो ये इसका Y component है minus J cap. इस minus sign को आप अंदर भी absorb कर सकते हो, so that we have this one as the we also have its Z component, so curl A का जो Z component है, that would be equal to Z component. So it is K cap so by this operation you understand कि given a vector and you have to find its curl, use this determinant for finding the curl, substitute the components of the vector and substitute the components of nabla or del operator, you get the curl. What is physical significance of curl of a function? The curl of a vector function or a vector field gives the rotation. It's also that we have seen this type of phenomena in nature. We have a whirlpool or a vortex in a say water body. पानी एक ही जगह पर घूमता रहता है, तो ये जो घूमने की टेंडेंसी है, this is the curl. This curl will occur wherever we have the rotating lines of the field. So in case that there is a situation like this, that the lines are like this parallel and they do not turn around, it is curl free. So I can say that electrostatic field is curl free. Curl free would mean that its curl would be equal to 0. So a curl free region is there where there is no rotation of the lines. When there is a rotation of the lines, that means the curl is present. And that rotational tendency sometimes gives this curl a meaning of rotation. So we may call curl as rot A. When I write in fluid mechanics, rotation of A, here it simply means that we are trying to measure the curl of that given vector field. So in this whole process of the lecture, we have understood that there are three very important operations which can be carried out with the del operator. If we place del operator and place a scalar function in front of it, we get its gradient. Gradient is nothing, it is the rate of change in a certain direction, which gets maximum when you move perpendicular to the level surface. Level surface is that where the scalar function has constant value. Then we talked about divergence. Divergence is the flow through a certain region. So if more liquid enters, less leaves, that means something is sucking the liquid. That region becomes a sink for the liquid. Its divergence is negative. If less enters, more leaves, it is giving a source of liquid, or it is creating some kind of outflow. It is giving out liquid, so it becomes source, divergence is positive. If whatever enters, the same amount leaves, it is zero divergence, divergence less. Curl is actually the rotation given by a cross product of del operator and a given vector field. It measures the amount of rotation in a given vector field. We have seen water bodies with rotating the water there rotates, जिसको whirlpool कहते हैं, vortex कहते हैं, the curl is present there. Right? If the curl is absent, the water or the liquid or the field lines will not make the closed circles, they will be straight. This was all in this, and you can follow the problems given here and solve them. Now you can pause the video and solve the problems as shown. Also, you can take some more problems of the same type related to this concept and solve them.